So today we're going to talk about writing invariants. So we'll talk about what an invariant is and how to write one. But basically what it is it's something that is like a formal way to describe what your program is doing. So basically like what we've been leading up to in this whole course, we've learned these kind of ways of, writing things formally, using our notation, like our logic notation, our set notation, things like that. And we've learned how to do proofs. And so, as I said earlier in the course, really our main goal is to be able to say things and prove things about the programs we're writing. So basically, that's what the point of today's lesson is really that first part is just saying things about the program we're writing. So let's just start with the definition of an invariant. So an invariant is a statement that is true during all steps of a procedure. So, so you could also think of this as your program, right? Like something that's true during all steps of your program. It's some property about your program that always holds, regardless of where you are, even if like the program hasn't finished executing. And the reason is that you want to kind of find an invariant like that is because like it is something that's true at step 0, step 1, and step 100 of your algorithm. But if it holds for an arbitrary step of your algorithm, this means it'll always hold. And so, it's kind of like that it's basically telling us something about our output. Like if it's, even though we're saying something about those intermittent steps, if we can prove again, kind of like our proof by induction, right? Like if we prove that something holds for the first step and that if it holds for one step, it's going to hold for the next step, then we can prove that it's always going to hold. So this is a good way to prove that some property always holds for your program, and therefore you can guarantee something about the output of your program. So let's talk about just like what kind of things we want to express about a program and how we might state that. So if you're trying to just say something generic about your program, like you're just trying to describe what your program does. And so I'm going to do an example of just like a program that finds the index in a list of the maximum number. So it basically goes through a list and it'll find the index, like the location of the highest number in that list. So for our algorithm, if I wanted to kind of, more formally describe what my algorithm is doing, I could say my algorithm takes as input list A. It outputs a maximum index, right? So it's going to output some value that's between 0 and the length of A minus 1, right? Because these are going to be the indexes of our list A. Our list indexes start at 0 and ends at the length of A minus 1. So it takes as input list A and outputs this index that's going to be some index, within the range of indexes of A. And what property do we want it to have? If it's the index of our maximum number, we basically want to say like the element at that index. So A at max index is going to be the greatest number, right? That's going to be larger than all of the other numbers in A. So now I can use my like formal way of, describing things to say that. So for all other indexes, J, let's say, for all J in that range, so 0 to the length of A minus 1. So this is saying for all other indexes, and this is actually including the max index, right? Because it's max index is going to be somewhere in this range, but that's okay because I have a greater than or equal to. So I say for all indexes in my list, max index, that element at max index is going to be greater than or equal to any number in A. So then, again, like this could be, J could be max index, and that's fine because it'll be equal to the maximum number then, and that's okay. So that's basically like how I would express this property. This is like how I could formally say that this is what my algorithm does. And so now I need to kind of, as I said, like this isn't really an invariant, right? This is something I'm saying about my output. But I want to have something that's true for every step of my algorithm. So how I would express that for every step of my algorithm is with this thing called an invariant. But I first want to get used to like this notation, because this is really what we're trying to say about our program. And then we can get into like how we express this using an invariant. So again, an invariant says something about your algorithm at every step of execution, not just at output. So I think the best way to really describe what the invariant is doing is by first looking at the algorithm of our of like what this program would be. So first, let's just look at some pseudocode of like what this program is, and then we could talk about like what exactly the invariant is describing after that. So I just wrote some pseudocode to basically go through a list and find the maximum, the index of the maximum element. So let's just like look at what this code does. Let's kind of read through it real fast just to make sure we understand what's happening. So our input is our list A. And so say this is A and these are all the elements of A. And what we're going to do is first, we're just going to decide that this first element, so the element at index 0, is going to be our maximum element. So I'm going to say my maximum index is 0 and my maximum element is that element, the element at index 0. And I'm also going to set n equal to the length of A, because that's just going to help me with my for loop. So basically my for loop is going to go from 0 to the length of A minus 1, or you could just say to n minus 1. And basically what I'm saying is for so I want to basically loop through every element in my list, and I say, okay, I look at each element and I say, if that element's greater than this current max, then I make that my new max element. And I store that the index of that element as my new max index. And so basically like so I first start off saying this is my max index, but then I look at A1 and I say, okay, if A1 is bigger than A0, then I want this to be my new max number. If it's not, then I keep A0 as my max. And then similarly, I go down to A2 and I say, if this is bigger, that's going to be, then A1 and A0, whichever's the max, then that's going to be my new max. And so I'm basically just doing that for every element. And so basically, if you think about like what's happening in this for loop, at like every point in this algorithm, like when I'm here at A2, I've now gone through A0 and A1. So you know that like at this point in the algorithm that I have the max is going to be the max of like this sublist, right? Like whatever I have as my current max once I'm at this point will be the maximum value, like wherever the max is in 0, 1, 2, that's going to be like what I'm going to have that stored as max elem when I'm at like this point in the algorithm. So basically like that's what your invariant's saying is like at every step of my algorithm. So like when I'm looking at A1 and I'm comparing it, to A0, like at that step of the algorithm, and then when I'm just looking at A1, the only thing I can say is, okay, so far, just this sublist of A0, this value is my max so far. And that is the largest number so far. That's true. And then basically like when I get to A1, I can say like, and I have done my step for A1 and then now I'm at A2, I can now say like, okay, now of A0 and A1, whatever that value is for max elem is true, but just for this small sub list, right? It's only true up to A2. It's not true for the rest of my list yet. And so basically what I'm doing is I'm saying some property kind of holds in every step of my for loop. And so I'm really saying something about this in this I that's kind of changing as I loop through. So I'm saying, for every element I, so I could say, or for every index I, that, or sorry, for every, here I'm calling, sorry, I should say I is like where I'm currently at. And so I is going to be kind of like if I'm at 2, my I is 2. And so basically for your J's are going to be like 0 and 1. So those will be like the previous indexes, everything I've looked at previously. So it's basically saying for all values up to this current index I, so everything, including I minus 1, so everything up to I, then it's true that like we have that max value. So we have some max index, right? Because we've defined some max index here. In every loop, we're updating our max index. So there exists some max index. And up to the point that we're at, up to I minus 1, it's true that all of those values are going to be either less than or equal to our max index. So basically, it's like this intermittent property. It's this property that's true, but only up to like wherever we currently are in our loop. So it's basically something we want to be true for every step in our loop. And I'll step through it more and so we get a better idea. So if this is like, if you're still like, what, that's okay. I'm going to step through it in a second. But first, let's just talk about like how to express the invariant. So I have like, this is my invariant, I want to say, basically for every intermittent step, for all j up to this I that I'm currently at, so that's basically whatever point I'm at in my loop, all elements are going to be less than or equal to the max index. The element at the max index. So it looks very similar to the property I was saying about my program, but now it's saying something kind of like intermittently. It's not saying something about the whole list yet. It's just saying something about where I am so far in my program. But it would look very similar to how we describe the property. So again, it'll say like my algorithm takes as input, and it'll have the same input. But now we're saying, and it behaves in a certain way. So we're not talking about the output because we want to talk about something that's true throughout the entire program. So again, we have the same input, list A, but now we're basically saying for all I, again, this is not it's not a coincidence that this I'm using the letter I, and I is the name of our index. We want that to coincide because that's what we're using in our loop. So for all I in 0 to the length of A, we have this max index up to I minus 1, such that every element that's less than I minus 1, so every element up to that value, right? So this is all of the indexes before I minus 1. We have this property that every element at those indexes is going to be less than or equal to the element at our max index. So this is what an invariant would look like. So if I wanted you to write an invariant about your program, it would be something that looks like this. That's basically describing the I within your for loop. So again, this is just me. I just copied the invariant over, but you might be wondering why I did it up to length A instead of length A minus 1, since my indexes only go from 0 to, the length of A minus 1. Why does my I go up to the length of A? And so, that's a valid question. And so I will be addressing that once, like in our example of like when we step through it, you'll see that I actually goes to like 1 more than the last index. So this is back to our example. So we have our algorithm and we have our invariant. And again, our invariant saying like for I in our A, like any, index wherever we are, everything before that is has already like we've found the max so far. And so basically like let's just try like plugging that in for actual values of I in our loop. So let's actually like run through our code. So like in our first iteration of our code, right, we've already done like lines 1 through 4, say, and now we're at like line 5 and I starts at 1, right? And so that's actually our base case. Our I is 1. And so you'll see like we're really at this point here. We're looking at this element. And I turned this element yellow because it's saying like, okay, we've already like looked at that element and we've stored it. So, so far, this is as much as we've like completed. This is as much as we've accomplished so far in our program. So for our base case of I equals 1, you'll see I plugged it in of like I plugged in the I equals 1. And so remember, this goes to I minus 1. So from the range 0 to 0, all j from 0 to 0. So again, like our max index, right now, our max index is 0 because we haven't gone into our loop yet. And similarly, that's all we like are looking at. So for all j in that range as well, like so for all indexes up to this point, so just right now we're just looking at index 0, it is true that this value is less than or equal to itself. Like, that makes sense, right? We've only looked at one element, and it's true that it's less than or equal to itself. But now let's like loop through one more step. So we do I equals 2. And so now, so we basically did one iteration of our for loop. So we stepped through, we said, okay, if A1 was bigger than A0, I made 1 my new max index. If A0 was bigger than A1, I made 0 my max index, right? And so either way, of these two, the max number is going to be the max of these two numbers. So now I can update my invariant to kind of correspond with that. So I can say now my I becomes 2. So now I'm saying there exists a max index in the range 0 to 1, such that for all of these values, for all indexes 0 and 1, that it's true that these are the values in these spaces are going to be less than or equal to the value of my max element, right? So like, if my max was A1, then, like say this number is bigger than this number. So if my max is A1, then it would be true, right? That then I would have, like in this step of the proof, I would have updated my value for max elem to be A1, and then I would have made my max index 1. And so then it's true that if A naught is or A0 is less than A1, this property is true, right? A at 0 is less than or equal to A at 1. And similarly, if A1, it's true that A at 1 is less than or equal to A at 1 because it's equal to itself. So it's just kind of showing that like this property is holding so far in my program. And basically what I can do is just keep going through my loop. So, when I get to I equals n minus 1, then I will, have done the list so far up to n minus 2. So I had that all these properties like have hold, for all the things up to n minus 1. But see, this is my problem, is I want it to hold for, I want to include this last term, n minus 1. And if you think about like our for loops, right, we do say like I goes up to n minus 1, but remember, like if I actually do my loop, so I set I equal to n minus 1, I step through my for loop, then I update I to be equal n, and then I go back to the top of my for loop and I say, okay, I is I is too high now, so I can't enter my for loop anymore, and then I continue down with the rest of my program. So that's kind of how your control flow of your program works. And so so the last value of I is n. We just don't enter the loop for I equals n. We just kind of go up to line 5 or say I equals n. Okay, well, that's not in this range, so I don't do my for loop, and I go down to line 9. So I actually do include I equals n, and then now I've shown that like that property holds for all of my values for I. And again, I just made n like the length of A. So that's the idea of an invariant. It's something that should hold at every step. And so again, like, just to kind of reiterate our loop invariant. And so, like invariant is often called loop invariant because it's describing really what's happening here in your loop. And so this is like, it's the part in the program, like it's describing this part of your program, basically, like this repetitive part. So that's why it's often called, your loop invariant. And again, like this is what I've already put on the, previous slide, but our loop invariant was saying for all I in this like loop, basically. But remember, we go to one more than where the loop ends. So even though this ends at n minus 1, we're going to be ending at n, and n is the length of A. And we say like there exists some max index up to that value, up to this I minus 1. And for all other indexes up to I minus 1, this max index is greater than that value. And so this is what a loop invariant would be. So basically what you're going to be practicing today is first maybe we'll describe what a program's doing, but then we want to say like, okay, what's the loop invariant at like this step of my program? And so that's what we're going to practice with today. And as you can kind of see already, as we were stepping through, we did have this idea of like a base case, right? And then we're basically saying, okay, well, if it's true here, then will it be true for my next step? And if it's true here, will be true for the next step, and so on. And so you kind of see how that kind of sets you up for a proof by induction, because you can prove it for your base case, so for the first value of your index, and then you basically prove like your recursive step. So like if it's true for n-1, is it true for n? Things like that. So you kind of see already how we would want to prove these by induction. But first, let's just get practice like writing these invariants out today, and then tomorrow we'll learn more about proving those by induction.